So now you guys know how to design an OTA. You know how to increase its DC gain. You also know how its gain is varying versus the sinusoidal frequency. Now what is the end goal of designing this OTA? Where do you want to use this OTA? In negative feedback. Now if you take this OTA or in general any system and put in negative feedback, what is one thing that can go wrong? If I take some system and try to put it in negative feedback, what do you suspect can go wrong? Stability. So this is now a single stage OTA. We have approximated it as a first order system. If I put this in negative feedback, do you think this can become unstable? No? Always no, or maybe sometimes it can become unstable. Sorry? Okay, if it's not clear, let's calculate it. So, okay, let me do this. So, let's look at what happens if you put it in negative feedback. Again, I'm drawing the standard negative feedback model. I'm sure you have seen this 999,099 times, whatever. This might be the 1 lakh time you are seeing it. So, here the gain A is now your first order system A of S. So, A of S is A0 by 1 plus S by P1. Right? So, here if I calculate the closed loop transfer function H of S, what will that be? This you have seen this before, right? So, what is the closed loop transfer function? Yeah, A of S by 1 plus A beta. Fine. So now you know what is A of S. We can substitute here, and if you do that, I think I'll directly write it. It will be A0 by 1 plus A0 into beta. Okay. Trust me, this is what you will get. So now now how will you decide if this transfer function is stable or not? If I give you a transfer function like this and ask if this is stable or not, what is the ultimate check? Poles should be? The pole should be in the left half of S plane. So here, do you think the pole is in the left half of S plane? Yes or no? Yes. And do you think this can go to right half plane? What is the closed loop pole? Let me write it clear. What is the closed loop pole I get? From here, what is the closed loop pole? P1 into 1 plus A0 beta. Let's assume A0 is really large. So how can I approximate it as? I'll say beta times A0 times. And this guy is in the left half of S plane, right? So do you think if I change A0 or beta, this can go to RHP? No. As long as I have negative feedback, which means A0 and beta are all positive, then this will always be in the left half of S plane. Is that fine? So, which means this is something you should always remember. A first order system, if you put it in negative feedback, what can you say about its stability? It will always stay. It's always stable. Okay. Cool. Yeah, maybe I can write this also here. So here, what is the closed loop 3 dB bandwidth of the system? This is the closed loop transfer function. You have the transfer function here. What do you think is the 3 dB bandwidth of the system? Sorry? Same thing, right? For a first order system, the pole location is same as your 3 dB bandwidth. Is this okay? So this is in turn equal to your closed loop bandwidth. Okay. Is this okay? So which means now I know that my single stage OTA I can approximate as a first order system, and as we just saw, a first order system if I put it in negative feedback, it is guaranteed to be stable. So that is one nice plus point about this one. It is guaranteed to be stable. But I'll put a hashtag because the first order system is guaranteed to be stable. But a single stage OTA, we are approximating it as a first order system, right? So if you are not careful, maybe some high frequency poles might not be really at very, very high frequencies. They can come to a lower frequency, making it a higher order system. But typically, this will be stable. So these are single stage OTA. This is nicely stable. So then what's the problem? So what do you think might be a downside with single stage OTA? We had already seen earlier what was one downside with using a single stage OTA. Huh? Yeah, remember that if I try to drive this guy, or if I try to use this guy to drive a resistive load, this is going to be a problem, because in our single stage OTA we are trying to increase the DC gain. And what have we been doing to increase the DC gain of the OTA? Increasing the output resistance. So now we have you might have designed an extraordinary OTA with infinite output resistance. The moment you put an RL here, it's going to go for a toss. So this is a problem. So only for capacitive loads you can use it. So that is one minus side. I'll say not great choice for resistive loads. And in practice you have to drive a lot of resistive loads. So now I know I can't directly take this RL and connect it to the OTA. So let me draw here. So now I have this nice single stage OTA, which I know is very good. You know how to design. But I cannot use it to go and connect to a load resistor RL. So how do you think I can drive this? Yeah, that's the simplest thing. Let's say you can try to put a voltage buffer, but let's not jump to conclusions. So if I put a voltage buffer here, how will you realize a voltage buffer? Common drain, source follower configuration. So you'll do something like this. You apply the input here, take the output from here, and here is where your RL is coming. And what is the small signal gain from Vi to Vo here? Gm times RL by 1 plus Gm RL. Now if RL is very small, this gain might not be 1. So this can be maybe 0.4 or something. Now you would have designed this, let's say, for a gain of 1000. Looks like if I try to have a unity gain, the overall gain seems to be reducing, right? So instead of using a block with a unity gain, what do you suggest I can do so that the overall gain is not compromised? Yeah, I mean, increase the gain of second stage, which means instead of having a buffer, we can put another OTA there, right? So that's what we try to do. We try to put another GM stage. Now of course this fellow, because we are loading it with a load resistor, the gain of this stage will not be very high, right? But even if it is, let us say, some 5 or 6, you see that the overall DC gain is significantly large, because you get bulk of the gain from this fellow here. This stage is existing only for driving the resistive load. So in a way, this guy here is sacrificing its DC gain to drive resistive load, so that this guy here can sit comfortably at the back and not have to worry about what to drive. So in a way, this is like nice protector protecting this guy from the resistive load. So I usually show this. It is like this. You have the resistive load. The last stage here is taking the grunt of it. It is trying to protect this guy, while the first stage is sitting behind comfortably, happily, without having to do anything. Okay. But that said, you have to design the last stage properly, because if you're not designing it properly for the resistive load, the gain of that stage might become very small. So instead of trying to preserve the overall DC gain, if you don't design it properly, the overall gain may drop. So this guy, instead of being a protector and protecting the DC gain, it might end up killing the DC gain, just like how the protector Kattappa killed Bahubali, like this. Okay. So make sure when you're designing that should be proper consideration. So let's move on. So now you know what to do with this. So let's say now you see that this gain is also not good enough. What do you suggest we can do? Huh? No, let's say you design this, you put one more stage, this gain is not good enough. That's all. I mean, it's like, Bollywood releasing sequels after sequels. You can also put one stage after the other to increase your gain, and you can keep doing it. Okay. So here the thing to notice, this fellow is the gain stage. The first stage is what is giving you the maximum gain, and the last stage is meant for driving the resistive load. These two are the main parts. If you want to get more gain, you can put stages in between. And this is the motivation for having a multi-stage OTA. Right. So if we don't have to drive resistive load, single stage OTA would be more than enough. But for driving resistive load, you have to have a multi-stage structure like this, where the first stage is providing the bulk of the gain, and the last stage is meant for driving the resistive load, and make sure that for this load, the gain of this fellow is not very low, right? Some reasonable number. Great. So now I know that each of these GM stages is a first order system. But now if I put multiple of them in cascade like this, overall system you cannot guarantee to be a first order system. So if you use it in negative feedback, what do you think can happen? This can become unstable potentially, right? So now let's see what are the conditions to ensure things are stable. And for that I'll start with the first order. We already looked at results for first order. I'll copy this. Yeah, so here this is the first order. If you have a first order system in feedback, this is what you get. And let me again write it here. The closed loop bandwidth is roughly beta times A naught times P. Now the closed loop transfer function here, I can rewrite it in this format. I will say that I have beta here in the beta, and what is this factor beta A of S? What is that called as? Loop gain. Everyone has heard this term, so that's what we'll define as the loop gain, beta times. Yeah. Okay. And if I give a feedback loop like this, how will you calculate the loop gain? You break the loop, but what do you do for the input here? Yeah, you make the input 0. It's a voltage source, so it becomes short, and then you can break the loop. This is an ideal block diagram model, so you can break the loop anywhere without any consequence. So I'll break the loop somewhere here, and what do? You excite the loop somewhere here. Let us say I feed in some test voltage here, and yeah, you see what is the voltage that is returning here, and the negative of this fellow is what we define as the loop. And in this block diagram, this is beta times A of S. So if I expand this, I know what is A of S. It is a first order system. So if I write this, this is beta times A naught by 1 plus S by P1. Okay. So let me try to sketch it. This is the magnitude of the loop gain versus frequency. At DC, what is the value of the loop gain? Yeah, at S equal to 0, it is beta times A naught. So it is starting with some beta A naught. and then you get the pole here P1. And remember, when we plot this Bode plot, things are in log scale, so I am actually plotting magnitude of loop gain in dB. So this is 0, but this is 0 dB. Right? And this frequency is of more physical importance, because till this frequency the magnitude of the loop gain is greater than 0 dB, that is, magnitude of the loop gain is greater than 1, which means you have sufficient feedback. Now for frequencies greater than this point, the magnitude of the loop gain is much smaller than 1, so it is as though the feedback is not very strong, right? And this point we call as the unity loop gain frequency, okay, omega u loop. So this is the, I'll write it here maybe, or I'll write it here, omega u loop is the unity loop gain frequency. It is the frequency at which the magnitude of the loop gain becomes unity. That's it. Matter of fact naming. And this is the loop gain transfer function, beta a0 by 1 plus s by p1. From this, can you tell me what is the unity loop gain frequency? Yeah, how do you say that? Correct? Yeah, very good. So again, the idea is this, as he's saying, typically omega u loop is much greater than p1. That is assuming basically a0 is large. I mean, if you have very small a0, you might have this, then omega u loop and p1 might not be close by. But I'll assume you guys are good OTA designers. You guys have designed good OTAs with high DC gain. So which means that assumption is satisfied. So since I am looking at frequencies greater than p1, I can approximate this fellow as beta a0 by s by p1. Now I am supposed to replace s with j omega, take the magnitude of this and equate it to 1, and this becomes equal to 1 at beta a0 times. Is this okay? And as you see, beta a0 p1 is your closed loop bandwidth also. So this is equal to the unity loop gain frequency. I'll put the unity loop gain frequency here. So this is something to remember. For a first order system, the unity loop gain frequency exactly equals the closed loop 3 dB bandwidth, which is in turn beta a0 p1, where beta is the feedback factor, a0 is the DC gain of your forward amplifier A, and p1 is the pole location or the dominant pole. And remember, this is true only for first order systems. That's what we have seen so far. Okay. Now one more jargon I want to introduce is the following. So here I have found the frequency at which the loop gain, which is beta times a of s, becomes unity, and that is beta a0 p1. Now if I try to find the frequency at which only a of s becomes unity, what do you think that frequency might be? a0 times p1. So that is typically what we call as the I will have to write somewhere, I will write it here. That is what we call as the unity gain frequency of the amplifier, that is a0 times p. This is the unity gain frequency of the amplifier or the forward gain you have. So I'll be using this notation consistently. When I say I'm talking about unity gain frequency, it is just for the forward amplifier I'm using here. And now when I use this amplifier in a negative feedback system or in a negative feedback loop with the feedback factor beta, the unity loop gain frequency is beta times the omega u. Okay. So if it's, this is basically your, fine. Is the notation clear? For the amplifier, I'll call unity gain frequency, and the amplifier is used in a loop with a feedback factor beta. The loop gain where it becomes unity is unity loop gain frequency, and that is beta times this value. That's it. Great. So now let's look at our, now we know the omega u loop. Let me write it. Omega u loop is beta times A naught times P1. And if this is our single stage OTA, let me quickly draw this. This is the output conductance and the load capacitance. This is GM. So here, what is the DC gain A naught? For the single stage OTA, what is the DC gain A naught? GM? What is the DC gain? GM by G out. I mean, DC gain, capacitor is open. I am looking at the gain from the input to the output. Okay. So this is GM by G out. And what is the pole location? G out by CL. That is the dominant pole approximation that we have done. So what is the omega u loop here? Beta times GM by CL. So as you see, for first order or single stage OTA like this, where you have the dominant pole at the output, the unity loop gain frequency, or for that matter the unity gain frequency, it only depends on the short circuit transconductance GM and the load capacitor CM. Okay. So because whatever we have been doing to increase the gain, that has been affecting only the output resistance. Now changing the output resistance increases the DC gain but decreases the pole location. Those two effects cancel. So which means now if I sketch the loop gain, let us say first I am using a 5 transistor OTA. It has some moderate DC gain, say somewhere here, some beta A naught, and this is the pole location. This is the unity loop gain frequency, which is beta GM by CL. Right. Now let us say I increase the output resistance of this 5 transistor OTA and made a telescopic cascode. Right. Nothing else changed. So only the output resistance has increased now. So if I sketch the loop gain for the telescopic cascode on the same plot, how will it look like? DC gain has increased, but what will remain same? This guy is remaining same, omega u loop. So this characteristics will also pass through the same. Oops. No. Let's say something like this. But the DC gain is higher, so this will keep increasing. This might be. Because if you increase the DC gain, the pole location also will reduce. Okay. So ideally, if I keep increasing DC gain, what is the value of R out? Ideally, what do you want for R out? Finite. So basically, this will basically, and if there is no R out here, this is not there, let us say, what is the transfer function from the input to the output? If I find V out of S by Vi of S, what do you think this might be? Here I am applying a voltage Vi. Resistance is not there at the output. What is the current flowing out? GM times Vi. Where will this current flow? Capacitor. GM times Vi, current flows through a capacitor. What is the output? Yeah, GM by. And what kind of a block has 1 by S kind of behavior? Integrated, right? So ideally, with an OTA, all we are trying to emulate is the behavior of an ideal integrator. Okay. Because remember, strictly speaking, I desire to have an infinite gain across all frequencies, but unfortunately that is not possible. So we try to do the next best thing we can do, which is to have an infinite gain at least at one frequency, which is DC. Okay. So that's what we try to do, and this is what it is. And here the omega u is Gm by C. So I'll stop here. We'll resume next week.